We're going to start with Hong-Ou-Mandel experiment. Hong-Ou-Mandel experiment is a landmark experiment in the history of quantum optics. And to motivate it, I would like to first ask you what you think about our quantum optics lab. I mean, you have done a few, maybe 3 sessions, and you guys have done all of it, I presume. Do you feel like there's anything in the experiment that makes you convinced of the presence of photons, the particle nature of photon?
I'm thinking you're asking about, is there any amnesia about the experiment?
There's a what? A visual?
Unpleasant about the experiment.
Unpleasant? Unpleasant. I of course I can relate with that, and but I like from my experience, because I've also run those experiments myself. My feeling is that I have not yet seen an experiment that convinced me of the presence of photons, the particle nature of it.
Even the GRA experiment, like we detect simultaneously this photon, which only happened if it's the particle nature.
Right. Yeah, the gating experiment, right? Yeah. Yes. That's why I asked you guys to do with both classical light source and the quantum light source. With a classical light source, you see that when the flux rate is low, you also don't have much signal coming through because the gating signal is just simply too weak, right? So to produce a zero coincidence count in such experimental setup, I think it's not too hard. You just need to have a light source that's weak enough to not trigger the gating signal efficiently, and you will have low coincidence. So for me, I feel like maybe there's still a loophole somewhere. That's why I asked you guys to do all 3 light sources to compare them. All right. We try to add.
You mentioned like do not get detect trigger the gate properly, but I think it's not the correct way.
Right. Of course, you need to trigger it to see the single photon nature, but that is more of like a background suppression, a technique for background suppression than like any to stimulate any physical process. You see what I'm saying? I feel like the gating is a technique to suppress background. And if you suppress it enough, then sure, according to the theory, the single photon signal will stand out. But I'm just saying that, of course, that is the standard interpretation. That's the standard thing to do. But like I said, the original GRA experiment is pretty straightforward and simple. The GRA experiment that we do using SPDC source, there's complication involved and like I said, when you pump this at different levels, the signal might not be as what you think it should, right? So there was like a lot of parameter control involved during our experiment, right? So I keep having this feeling that we really need to do something that shows the particle nature of photons, and that's why we try to add this landmark Hong-Ou-Mandel experiment. But unfortunately, we have tremendous physical difficulties so far and we have not yet succeed in building it and demonstrating it in our lab. But today I want to start our discussion with this experiment, just to understand this experiment conceptually, to see why this is sufficient to show us the particle nature of light. Okay. All right. So in our lab we have the alignment laser, right? And the alignment laser is basically a beam splitter, right? No, sorry. The alignment laser plus something called acetone. So this is our laser, and this is 633 nanometer. So it sends light in something called acetone. It's a prism that is made to split the beam. So it's basically a beam splitter. Split the beams symmetrically, right? If we take one light source and send it to an interferometer, right? So let me just mark it like this. If we take it and send it to a beam interferometer, let's see. So microsecond interferometer, right? And detect it at one port. What do you see? We see an interference fringes as we move one of the mirrors, right? So we see an interference fringes. When we do this with BBO, so this is essentially a single photon SPDC source. Okay, so this is also a laser for 5 nanometer. Also get 2 beam out. Okay, supposedly we have a single photon. Okay, so let me write like this. And we send it through the send interferometer. What do you see? You also see interference fringes, right? So they are the same. Can we do something that show just like complete different signals without additional? I mean, if I hide this in a big block box from you, right? Can you distinguish the light source? Well, with this measurement, you cannot, right? And of course, I said it before, because such a measurement does not involve the photon operators in it, so they cannot distinguish different photon statistic. That's correct. So we ask ourselves this question: is there really no way to distinguish a single photon source and the classical coherent source using interferometries? Do we always have to do correlation measurements? Well, in Hong-Ou-Mandel experiment, they did a little modification. They have a little modification from what we have here. So let me start with this. When you have light that go go into two detectors. What do you see? In terms of coincidence counts, you see a flat line, right? Uncorrelated. Now, let me ask you, if you do it like, if you put a mirror here, be careful with the drawing. Okay. This is a terrible drawing. Okay. If you put a mirror and a beam splitter, right? And this goes to here. This goes to here. Does it change your result?
Is it a mirror so there is no black light?
Yeah. It's fully reflective.
Yes, there should be.
Should there be any difference in your result? And what difference do you expect? What difference do you expect? Well, I don't expect any difference because, I mean, light like a split is still light, right? So you have one beam split like this and the other beam split like this. And of course there is cross turns. Yes. Okay, so you will see, sure, you will see you will probably see, so here. Let's see. So suppose the intensity is the same. Previously we see this. So detector 1. Detector 1. Okay, so this is detector 1. This is detector 2. Okay. We see detector 1. Previously we see detector 1 as like a line, right? And we see also a flat line in the coincidence counts in the correlation measurement. Now with the implementation of two mirrors and one spin splitter, sure, we probably will see if there is a little phase difference, we'll probably see a higher level of light, right? Or a lower level of light. But if we don't move it, it should stay as a flat line, right? But for coincidence counts, I'm still expecting to see a flat line, okay? Because what gets in here is just, it's just the same coherent state, but with a different amplitude, that's all, right? So intrinsically, there's really not much difference. However, if you do this, let me see. Okay, let's see. If we have a different source, then of course we expect to see a bump, right? Because they are created in pairs, right? So they will arrive at the same time, right? Okay. Well, anyway. So there's supposed to be a positive correlation, okay? Now, when you do this, okay, what do you expect to see? Huh? Zero? No coincidence. Why is that?
It will be either or, either both going to same detector. That's the only thing.
Why? Why can't you just have one going this way and the other going this way? I mean, that's also possible, right?
Yeah, but 2 times opposite with opposite sign will be.
How do you know 2 times of opposite signs?
When you are doing that one expanded.
Huh?
Single photon.
Okay.
And so maybe you want to mention about the newsletter when they polarize in the newsletter. And there is the, maybe he mentioned about the phase difference.
No, both will be same phase. So
On detector D1, on the single detector, I mean, this is really just the same as this interferometer, right? So the behavior should be identical, right?
in D1 it should be.
No, if we do not modulate, this is if we modulate. If we modulate the mirror in time, right? If we modulate the mirror in time, yes, it will oscillate. But if we just keep it fixed, then it will stop at either a high value or a low value. Okay? It will remain there. What I'm trying to say is, from the interferometric measurement, it looks like we should get the same result. So if you have the delay that is set up to cause, maybe like a pi phase shift, then you are expected to get a lower signal. And if the phase shift is constructive, you will expect to get a higher signal. So it should be identical to the coherent laser measurement. Okay, but what about this? Well, here, intuitively, we think there are several possibilities, right? We could have this photon get reflected from this, from the beam splitter, and the other photon go through the beam splitter. So here you can have 2, 0. So the first place indicate this port, and the second place indicate this port. Okay, so this is just mode labeling. Okay, So we're expecting this, and on the other hand, here we're expecting this. Okay? But we also think this should be possible, right? One go through, the other get reflected.
Yeah, but the means yes, that is possible, but there is like that is possible in two ways, right? Like the first one get reflected and second one to get transmitted.
Yeah.
And the other way.
Yeah.
So
there are two ways.
Opposite will come.
How do you know it's opposite?
Because like it has both has a phase of phase difference is fine.
How do you know?
Because it's like getting translated and reflected. So that
can it be positive?
These both should happen.
Mm-hmm.
These both should cancel.
Well, if you have not read any quantum optics textbook, would you expect the sign to be opposite?
Because beam splitter is like A plus B into A minus B, right? And since these are two independent states,
what is the reason? What's the physical reason for that? You keep telling me textbook results. I don't want that. I can read the textbook myself. Others can read textbook themselves. I'm asking you, if you give me this answer, do you have any insight to already know that there are going to be a phase difference before any further discussion? Like, just given what we have here, do you expect the phase to be different? I don't know what it would be. Maybe positive, maybe negative, I don't know. Okay? But intuitively, I think, like I said, intuitively, I will expect that there are all these possibilities. And like he said, there are indeed two possible ways to get one photon here and the other photon here, which is, so we can get this photon reflected to this detector and this photon reflected to this detector, or we can have this photon transmitted to this detector and this photon transmitted to this detector, right? And of course, the photons are indistinguishable, so these two processes are also indistinguishable, okay? But I don't know about the phase relationship. I don't know any of that, okay? What I'm saying here is that what I see here is that I think the two ports should have like identical signals, and thus I wouldn't expect any, just like before they have identical signals. Here, when I change my measurement schemes, right, just like we reroute the photon path a little bit, I would expect that I would see the same signal as before, okay? And of course, this will be, sure, I give you that. So when you have these things, one going here, one going here, you have the same positive correlation as before. And if you have this, then you have negative correlation, right? So you don't get two clicks at the same time, right? Either one click or the other click. They don't click at the same time. So I would expect this. Okay, so maybe I do expect a little difference. I expect two different contributions, and I expect that my data will be like a mixture of both. And I expect that eventually I'll get this. So maybe going from a positive correlation to an uncorrelated, like a flat correlation. That's what I would expect. Okay? So if I have a click here, when a click here occurs, when they both click at the same time, then I have a count in the coincidence, right? But if they don't click at the same time, then I have zero coincident counts. Therefore, you have a dip. Okay?
How about
1-1 means one go here and the other go here.
yeah,
They click at the same time.
Yeah.
Right, so that gives this.
Okay.
Okay, so this is what I would expect from 1-1. And this is what I would expect from 2-0. So I expect both signals should be present in my detector. And as with time averaging, I should have a flat line. That's what I would expect. Okay? So maybe yes, with such a setup, we can see a different result between the coherent laser and the biphoton source. All right. Now, so without further discussion, it seems like such measurement schemes although we're still using coincident countings, okay? But we're not gating or anything or doing anything like that, okay? And it seems like it might be possible to use such a measurement scheme to distinguish between the coherent light and the biphoton source, okay? And this is the experiment that Hong-Ou-Mandel did. So there are 3 persons. I think Mandel is the advisor. Okay. So what they find when they did this experiment, they find a result that is actually, so this is what we expect, right? They find a result that is even more surprising. They find this. So instead of a flat line, so the classical light give us this flat line. Oh, right, actually. Let me come back to here. If we do have a flat line, right, then this cannot then such measurement cannot distinguish between the classical light and the biphoton source. Okay, so yeah, so this is a classical result. But anyway, when they did the experiment, they found that there is actually a dip instead of a flat line. And they give an explanation for this phenomenon. And this explanation involves 2 photon states. Okay, interference between 2 photon states instead of interference between 1 photon state. So the measurement that we did with the microsecond interferometer, that is interference with 1 photon state. And that does not have a different result than the classical, than the coherent light. but the interference between in the two photon state can give a different result. Okay, so so their result was seen as like a smoking gun experiment to prove to show that the light indeed exists in the photon states. Because when you think about it, if you just have the classical light, the coherent laser light, there's no such things as, I mean, we like forget about all your quantum optics learnings. If you just think about the coherent light, the classical coherent light, there's no such things as two photon states or one photon state. There's no such things as photon states, right? So like the existence of photon states needs to be shown, and such a measurement shows the difference. Okay. And this is, here I'm gonna give a quick derivation for its explanation. And that involves, so it turns out that the beam splitter is a device that couples couples modes from different how do you say? So you have mode from here and here, right? And yeah, that's a good question. Different mode. Usually we define mode by k vector, right? So you feel like this and this are the same mode. Yeah. Okay. That's a good question. I don't know. Okay. But through this experiment, they found that okay, maybe I can say this. This mode, the reason this mode and this mode is different is because when light goes into this material, it scatters or it regenerates, right? So when it regenerates, then that is considered a different mode. Okay, maybe let me start with that. Okay, so this is, so the source, so this mode, the source is from your light source, but this mode, the source is from this material. Okay, on the material. Let me give labeling to this mode. This is labeled as 0, 1, 2, 3. Okay. So what they found through this experiment is that a beam splitter is a device that couples different modes. And so you can see this as like input and output. That couples different modes. And after the coupling, the operator commutation relationship needs to be maintained. Agree? So what does that mean? That means A1, A0, A3, A-3, A-2. Before we have A0 and A0, that is 1, that's 0, right? And A0, that is 1, right? And we have between different mode. So within the same mode, if you have dagger, that's 0.
Different mode, everything will be 0.
Yeah, and raising, that's 0. Lowering, that's 0. But if you have raising and lowering, that is 1. But between different mode, it is always 0. Yeah? Okay. So they found that the beam splitter is a device that couples different modes, yeah. And in order to maintain, for the creation and annihilation operator to maintain the quantum mechanical property. So because this is the quantum mechanical property, right? This ultimately has to do with the quantization of light. Remember? When we talk about quantization of the E field and the B field, it all boils down to this, right? So in order to maintain the quantum property, the commutation relationship needs to stay intact. And because so generally you can assign like transmission coefficient and reflective coefficient, and there can be complex number because not only the amplitude is splitting, you can also attach a phase to the reflected light. So there's that. And so in principle, the coupling could have like different coefficients. Okay, there are 4 possible. So from this side, you could have refractive and transmissive coefficient, and from this side you can have a different refractive and transmissive coefficient. And in principle, they can be complex numbers. So there are 4 of them, and each one has like real part and imaginary part. So you have in total 8 parameters, 8 free parameters, yeah. But because of this photon commutation relationship, so this is like before the beam splitting, and after the beam splitting, of course, you are expecting them to stay the same, right? So, for example, 2 should be 0 and 1 and 2 and 3. You're expecting this, right? I mean, they should just have the same properties. Between different mode, the commutation relation is 0. Within the same mode, it is 0. If it's the same, it has the same form. But if you have raising and lowering, then it's 1. So anyway, so this quantum property of light restricts the property of the A parameters, and all boils down to like an equation. And for the reflective and transmissive coefficients on both sides to satisfy this communication relationship, there are different combinations. One of them is this. So this is basically a pi over 2 phase. Okay? Okay, so assuming this is a 50-50 beam splitter. right? So this is one of the possibilities. There are other possibilities, okay? But let's start with this. This gives you that okay, so just a little bit of algebras. Why do we wanna express 0 and 1 in terms of 2 and 3? Because we start in the Hong-Ou-Mandel experiment, we're starting with one photon here and one photon there, right? So that is a state described by this, right? So 0 and 1 denote the port, and 1 means one photon, right? This state can be written as this. Okay, this is just the vacuum state. Okay, and vacuum state is basically 0, 0, 0, 0, all of them are 0 for 0, 1, 2, 3, all the modes. Okay, so this is just like a shorthand of a lot of zeros. Okay. To see how these states transform after the beam splitter, we must replace the creation operator of the 2-port by the racing operator of the other 2 ports. Okay, so that's this. Yeah, and you can carry out the expansion. It looks like this. Okay. Then you have the operators operating on the state. Okay. All right. Now we see that here the imaginary number result in this minus sign here, right? And that gives a phase difference between these two photon states. Therefore, these 2 photons, they cancel. Yeah? Okay. now we can track using, sorry, this is plus plus. We can track what these states represent. So the two here give you 1 photon here, right? And this 2 comes from this. Yeah, and this comes from this. Okay, so what that means is here you have 2 coming from the 0 port, and 3 coming from the 1 port. Okay, so these are the direct transmissive process. On the other hand, here the 2 comes from here. The 2 comes from the 1 port. Okay. The 2 comes from the 1 port, so that's this process. And the 3 will come from the 0 port. That's this process. Okay. And this 2 process has opposite phase, and they canceled. Okay. Now, if we ponder about this result, I think there are 2 things that, yes.
To make sure why there is a phase, you use a red pen to point the.
Mm-hmm. Yeah. So in principle, this could be any number. Like I said, there are 8 parameters, and these 8 parameters are restricted by the photon communication relation of the field operators.
Some kind of, I just meant is a constraint. So
Yeah.
8 parameter follow this constraint.
Right.
Get the result like that.
This is one possibility,
One possibility.
right? This is one possibility.
It's also possible like A0 plus A1 and A0 minus A1, right?
That's another possibility.
Without going.
That's another possibility. Okay. All right. Although with that possibility, you will still have a minus there.
Yes.
Yeah. Yeah, but you will have, okay, sure.
There
Yeah.
won't be any I,
Yeah.
but the
Yeah.
minus will be.
Yeah. He's saying that, how about 0 plus A0 plus A1, A0 minus A1? Is that a possibility? Yeah, looks like it could work. Yeah. Anyway, there is like, so if you go to a quantum optics book.
Only difference will be that in the second stage, it will be minus sign.
Yeah.
It's 2, 0, minus 0, 2.
Yeah.
Can you just list some, I mean a few of them?
A few of them.
Yes.
I don't know. I need my book. There is, so my favorite book, my favorite quantum optics book is by Jerry and Knight. And there is like this general equation that give you exponential I, phi, exponential theta. So they use phi and theta as parameters, and there are just like a lot of possibility. Okay, so I strongly recommend that if you want to have more examples. But like he said, plus and plus 1, so 1 plus 1, 1 minus 1 that seems to be working too. Okay. All right. But the point that okay, so these are just like technical details. Let's focus on the physics. I think there are two things that are interesting to us here. Okay, first of all, this is a phase difference between a two-photon state. Sorry, not a two-photon state, not in terms of two photons in the same mode, but it's more precisely, this is like a two-mode state. Okay, so single photon in two modes. And I think the fact that there is the phase exists, like there is like a interference, like there's a destructive interference exists between such two mode states. That appears to be. Do you feel like there's no classical counterpart to this?
Actually, I think the way we mentioned about destructive interference is already involved the restricted properties.
Right.
Yeah.
Yeah.
It's like the phase shift in the
Right.
reflection of the
Yeah. Okay, so you're saying, yeah, sure. I feel you feel like having a destructive interference is not a biggie, right? It's not like too surprising because if we just think intuitively, the beam splitter introduced some kind of phase shift, and it combines beams. So sure, there should be some kind of interference occurring, and this picture, we can also roll this picture for classical wave, right? Yeah. So maybe the interference between these two are not too surprising. Okay. Sure, I give you that. How about the other point? Another point is that I think that the point, sure. So if we don't focus on this part, let's focus on this part. I think that the other pore, one pore is completely depleted. The fact that the other pore is completely depleted, that is a result that does not show.
Classically, reflection will not change phase, right? Classically, a reflection will not change phase.
It could.
When you use a mirror, you
yeah,
don't
it could.
Add phase?
It could. Yeah. The coating can have certain properties such that it does that. Yeah, that's no problem. For example, you can have like a multi-layer dielectric mirror, okay? And the reflection is by interference between different layers. So your output light could have a phase difference from the input light. So that is possible.
Yeah, but that's because of the path length, right?
Yeah, but I'm saying that to give a reflected beam, a phase that is a phase difference from the input beam that is possible for the classical light. That's not unique to quantum property.
Like, in sense of like, if there is a addition of like the addition in the path length.
A broad picture is, for example, you go from the less, it's like a string, right?
Like an oscillator?
Yes, or just like a string. And when you have like a very dense density, like you will like it's when you short it, it will the wave when it's reflect back. I mean, because you go for example, okay. The correct word is about the refracting.
Refraction? Refraction?
Yeah, I know refraction can add some phase, but if it's like a
When
refraction.
you come when for example the light from the less refraction.
Yeah, refract. There is reflecting and refracting. Refract means the angle changes a bit in the transmission.
How you call it?
Reflection?
Yes.
There's reflection
Refractive index.
Refraction.
and refraction.
Come from the less refraction index to the higher refraction. You will get the reflection.
Index of refraction.
I mean the fact in that condition.
That I understand, but
Oh, he's talking about Fresnel's
I'm
equation.
talking about reflection. Like if it reflected at the same angle, the refractive index doesn't change.
Reflection. You mentioned reflection.
Reflection.
But reflection property depend on refraction properties.
So you're talking about going from one media to the other media. Yes, you have the transmission and you have the reflection, right?
Yes.
And both could pick up a phase according to the Fresnel's equation.
Yes.
That's what you're talking about, right?
Yes.
Yeah. Yeah. So depending on your wavelength, right? And your angle.
Actually, depend on the refraction index and also the correlation.
Okay. Right. Anyway.
But that is between R and T, right? Or incidence and R.
Yeah, but this result is between R and T, like a cross product between R and T. Okay, what's the question here?
It is not there is no phase shift when the light reflects back from the incident.
There could be. I mean, the fact that you have a -1, that is the phase shift right there, right? Anyway, phase shift is not a quantum property, all right? So that exists for classical wave as well, right? But let's just look at the fact that, okay, that's not, like you said, interference exists in classical wave. So without going into much technical theoretical details, this result would not surprise you. Yeah. I agree. Okay. But how about this? What surprised us is one port is completely depleted. One port is completely depleted.
So they go together to the same direction after.
Right. Yeah. If there's no photon, right? If there's no photon, if photon does not exist, we only have classical wave. You cannot have one port completely depleted. Of course, you can adjust. You can adjust a phase, right? But it's not gonna work for all mirror positions. But this works for all mirror positions. It doesn't matter how much your delay is. Okay? It doesn't matter how the phase difference between the two ports. You always have 0 on one port. So the fact that you have 0 in one port, that means the light are in a sense countable. You can
But we cannot say one is you mentioned about the internal phase difference, but if we have external phase
I'm talking about even with the external phase difference. Yes, with classical wave, you can arrange such that on one port you have no light, and the other port you have light, right? So that's destructive interference. But when you move your mirror position a little bit, then that you move away from that destructive interference point, and light comes back, right? But what we see here, or what we see here, okay, this is a result. This is a consequence of two physical results. One is the relative phase difference between the two photon states, and the other is one port get completely depleted. Yeah, okay. So these two physical process, one has a classical analog, but the other one does not. That's what I'm trying to say. The other one does not. Independent of your phase shift, the other one always have 0 on one port. And of course, it's not like always 0 because on detector 1 and detector 2, as a function of time, you see they have the same count. So it's not like this dip is not because you are locking photons in one port. Yeah?
It should.
But
it should go down and up.
No.
Because at the same.
Your raw data from the detectors are the same. Okay? But the coincidence there's 0 coincidence. So that means one port get completely depleted when the other port has signal. And when the other port has signal, this port get completely depleted. And this can happen if and only the photons can be counted. They are like countable entities in the light field. That's what I'm trying to say. Yeah? And if we can manage to do different input states, so instead of 1 and 1, we can do, for example, 2 and 0, and 3 and 1, or 2 and 1, like different combinations. All these combinations, turns out, it will all give you, some of them will not have a dip, but all of them will have different results. It is very sensitive to your input photon states. They all have different signatures. Okay, so the generalized Hong-Ou-Mandel experiment all have different signatures depending on your input states. And that just, I think that shows that, so if you are ignorant of the quantum optics theory, just by seeing that experimental fact, that by preparing your input state differently, okay, you can have like such dramatic change in your signal. I think that shows the particle natures of light. Okay, because if light does not have the particle nature, or this specific light source does not have the particle nature in it, it only has the wave nature, then what you do at most is just to change the ratio between the two ports, change the intensity ratio between the two ports. And that's not, according to classical theory, that's not going to give you such a dramatic change in your experimental signature. Okay? So that's why I think the Hong-Ou-Mandel experiment is the experiment that does shows the particle nature of light. Yeah, you have a question?
Because it's a mass derivation. I want to ask if there has any physics picture like the photon interact with the electron in beam splitter, or we interact with what. So like I know it's not a cool pair, but what like
You're looking for the bosonic picture?
Critical temperature, under critical temperature, you have a pair, right? But it's interaction.
I think Tom is looking for an explanation for why there are two in one pore and not the other. Okay, it is very tempting to see that, to go with the following picture. So because photons are bosons, so if you have one photon coming here, the other photon coming here, this photon will want to follow this photon. Wherever this photon goes, it will go with it. So if this photon go like this photon will go with it. Right? That's 2, 0. And if this photon go here, this photon will go with it. So that's 0, 2. Is that the physical picture you're looking for?
Yeah.
Okay, that's not true.
I think he mentioned about some interaction.
What?
Interaction picture.
That's he's looking for this bosonic picture, right? This is what you are thinking about. All right. So like I said, yes, it is very tempting to think that this is what's going on. So, like I said, one photon follow the other photons, right? When this goes here, it follows it there. When this goes through, it follows it to this port. So you always have 2, 0, or 0, 2. If this will be the case, then inputting 2, 0, you will have just 2, 0 or 0, 2, right? Because if they are stick together originally, they will not want to separate. If you go through the math again, so starting with 2, 0, okay, you can do this exercise yourself. You'll find that the output state will have 2, 0, 0, 2, 1, 1, and the 1, 1 does not cancel. So you have all kinds of results. And if you input, for example, 2, 1, right? So just adding one more photons to 1. With that pictures, you will expect 3, 0 and 0, 3. Yeah? If you run this math again, you'll find that that's not the case. You have 0, 3, 0, 2, 1, and 1, 2, and 0, 3. All four will be all there. Okay? So the fact that we have 2, 0 and not the interference term, this is a kind of coincidence. This is like just a very misleading coincidence. Okay? It just so happened that the cross term cancels, and you have only this term left. But with the different input states, generally, you have more terms. Okay? Nevertheless, this does not change the fact that I said that when we have different input states, so photons are supposed to represent the amplitude, right? So if the amplitude are not quantized, does not have this quantized nature, if amplitude can be changed continuously, then at most we're just changing the relative amplitude of the two ports, right? And it should have, maybe a little bit of, if we change, amplitude here a little bit versus here, it shouldn't affect this too much. And it shouldn't affect our correlation measurement too much. That's what we will expect from the classical wave picture. But the quantum the experimental fact shows us that as we change the amplitude just like a tiny bit, like I said, 2, 1 and 1, 1 give very different result, right? If you have 2, 1 instead of 1, 1, this dip will not be there. It will go up. So you have like dramatic change when you just change the field amplitude just a tiny bit, okay? So that shows that the amplitude, the field amplitude, has a quantized nature. And that unit is very, very small. Okay? So I hope this, I'm not very good at explaining this. I didn't do a good job in past semesters, so I hope I'm doing better now. But I hope that this will give you a feel that you know, the quantum nature of light is really there. What is the quantum nature of light? It's in the amplitude. It's not in the mode. It's not in the polarization. It's in the amplitude. When the amplitude changes a bit, then like the experimental measurement result could be drastically different. Okay, so that's what I'm trying to get this to. All right, let's take a short break, 5 minutes, and we'll come back to our delay choice experiment.
They struggle, right?
I think so.
Yeah, because last time I remember they mentioned they will go to China. Yeah, because this like near the end.
Yeah, so that's why they went to Hong Kong to get the visa.
Oh, okay, I see.
Okay. I didn't know they go to China, but
Actually,
like I know
don't
people.
visa.
I know people who goes to Hong Kong just to get China visa.
Oh, really?
Because you cannot get the visa from Taiwan.
Oh, okay, I see.
So like most European can go to Hong Kong without any visa.
Oh, okay.
So they could go there,
So
get the visa, come back.
Oh, okay, I see.
I know that, but I don't know whether Simon and Vida did that.
Yeah, they did. Because Vida went to Hong Kong first and then Simon?
I don't know. I thought both went at the same time.
No, they separated out. First, I didn't know about the visa requirement.
Because I have some international students friends here.
Oh.
One of them went to Hong Kong for the visa.
Oh, so
China
you
visa.
mean like as long as we go there, then we can like take the visa easily?
No, because from Taiwan you cannot apply for China visa because there is no.
If there is
there is no embassy, China embassy in Taiwan.
Oh really?
Yeah.
Okay.
So you cannot like.
So
from Pakistan you cannot apply for Taiwan visa. So I know Pakistani students come here, they apply for in UA or something embassy, Taiwanese embassy for Taiwan visa. Go there, go to the embassy and apply for visa.
Okay.
You understand? Like if there is no embassy in that country of another country, you cannot get visa directly from that country.
Oh.
You have to go to a country which has the embassy to get the visa.
Why not? Why Taiwan don't have?
China say it is its part, so they don't they don't want an embassy in their country.
But they can come to go because they still.
It's not like people from here are banned there.
Okay.
You can go there. You can apply here.
Okay.
Okay, I see that you all have rested. So let's start. Am I starting with 5? Board number 5? I think yes. Anybody remember?
Yeah, 5.
Okay, thanks. All right, 5. So let's start with this. So around 1970s, when in the early stage of quantum optics, people were still thinking about the nature of light, especially the particle nature of light. Like how does it work? And of course, in the meantime, people are also trying to understand how does like electron work, because they have this interference fringes from the electrons, right? From double slit experiment. So it's a mystery at that time. And John Wheeler, who is the PhD advisor of Richard Feynman, the famous Richard Feynman at Princeton, have a series of thought experiment called delay choice experiment. And this thought experiment were realized later, but the purpose of that was to test this idea of photon, light as, like a concrete particle traveling around across space-time. Okay? So he used a very drastic, so in his experiment, he used a very drastic light source, which is a remote start. So suppose we have a remote start, and the remote start emits photons, right? In different directions. Let's say 1 at a time. But it could go different directions. So like here and here, different directions. And suppose this, this photon, if it chooses this direction, because now we're trying to test this we're trying to work on the assumption that photon is like a solid baseball that travels across space-time, right? So if the photon take this direction, it does not take that direction. Yeah? So either or. All right. And he's saying, okay, now assume that we have Earth right here. So this is Earth. And we receive these photons, right? And suppose there is like a distant galaxy or something, okay? Like a cloud of interstellar dust.
The source is the star, so it's thermal.
Yeah, it doesn't matter. He's trying to say if light is particle, so he's trying to work on the assumption that if light are like particle, like baseball particles, that are emitted 1 at a time, right? So forget about all the quantum optics that you have learned, because those are not developed at that time. The particle nature of light was it's like an onion. It was discovered gradually through a lot of theoretical debates, theoretical trials and errors, and experimental confirmations, and like a lot of things. It's a combined effort to learn that light indeed has that particle nature. Okay, but I wanna bring you back to the early stage of quantum optics, and let's start with this naive picture, physical picture, that light, like when we talk about particle or wave, right? We know that light could work as wave. That's no problem. Maxwell's told us that. But what if light works as particles? If light was generated as particles, okay, maybe it can be generated as wave or particle, just like, I don't know, yeah, animals, animals could be born with wings and or no wings. So either fly or no fly, not fly, right? So maybe, so like they don't know how this wave particle, how to reconcile this wave particle duality at that time. But suppose light is generated either as wave or particle. Okay, so let's work based on that assumption and see what will happen. Okay, so let's say if light is generated as a particle and it takes this path and it reaches the Earth. Okay, then we will see in our detection screen, a mark. Yeah. Now, suppose there's a remote interstellar object, and through the gravitational lensing effect, it could bend the light such that it also reach Earth. Okay? What would this do? Well, since it's coming from a different angle, you will likely produce another point, right? So if we have a screen on Earth and we just like wait for the light, for the particle of light to fall from heaven, then we should have different spots, right? And it's just like randomly distributed on the screen. Okay, cool. Now, now he's saying, okay, suppose that the light was generated from this start, maybe like a year ago, and it takes 2 years to travel to Earth, right? So like by the time it finished half its journey, it's already like very far from the start, 1 light year away, okay? So whatever you do here, or whatever happened here, does not change the nature of this particle. It doesn't change its direction. It doesn't change. You shouldn't be able to do anything to it. It's outside of your light cone, per se. Yeah. So at this moment, if we choose to have a different measurement scheme, so instead of just having a screen here, what if we place a few more optics, okay? Such as, for example, mirrors, yeah? Such as mirrors, and we can reflect light. We can steer them from different directions. We can have lots of mirrors and steer them from different directions, and eventually combine them with a beam splitter, right? And then we look. What do we see? Yeah? In principle, if light is a particle that travel in space and time, that travel across space-time, then whatever we do here should not affect its nature, right? So if it's generated as a wave, it remains as a wave. If it's generated as a particle, it remains as particles, right? So if it's a particle, then we should probably expect just one dot, right? Because now we combine the two paths, and that should be it. Just like one dot, okay, or one blob. Okay, so let me draw a more realistic. So one blob. Okay. Now, if if light is generated as wave, then this construction should give us not one blob, but a blob with fringes, right? Okay. What? So I'm saying if light is generated as particle, it should give you like a blob. Okay? And if light is generated as wave, it should give you fringes on top of that blob. Blob? Is blob an English word? Lump. Maybe I should say lump, like a lump, a bump, just like a spot, okay? All right, so the question now is, would it make any difference to my result if I choose how I measure it? If I choose to measure it without this additional optics, then I see two spots. If I choose to measure with two optics, do I see this or that? Since the photons has left its source long ago, and it will take another year for it to arrive at the detection site, it shouldn't matter what I do with the measurement setup, and the result should always be the same. So if today, I do measurement like this, and the next minute I do measurement I take out the optics, it shouldn't change the result, right? So this is called the delay choice. The choice is in the choice of measurement scheme, okay? Or if this is too much trouble, we could even do this. We could even put a polarizer here, yeah, and we can set in at different settings, right? 1H, 1V, right? And you will expect that if it's particle, then you always see this. But if it's wave, right, you will see this when they have different signs, but you will see the fringes when they have the same sign, the same polarization, right? So just by turning your polarization axis in real time, right? You can alter, like we are supposed to be able to alter between two different results. But that is only true if it's a wave.